good morning once again. So now we are moving ahead, and this is our last lecture of this Gyan course. So now I request Andre to start with this talk and conclude our final lecture of this Gyan course. Thank you.
Okay, let's consider, let's continue and consider also some theoretical points, and so we have seen that the PCM device performance can be influenced by material parameters and by device geometry. Here we can do a lot of things, like improve thermal stability of amorphous phase, to try to reduce crystallization, melting temperature, improve crystallization speed, quenching speed, resistance, drift, thermal conductivity of both phases. But let us look some different points. I cannot consider everything, but one interesting consideration on the device side is how to improve the electrode materials, how to improve this also, like on material side of electrodes. The problem of electrodes, standard use titanium nitride electrodes for switching, and they have thermal conductivity in this range. It's not so large, but the tungsten is used also as heating element, so it's very high in both materials. So and the thermal conductivity of these electrodes, they're huge compared to the PCM. And this is one problem that such electrodes, we have a huge loss of thermal energy, and this causes more than 2/3 of the heat lost and lead to large reset currents. So now let us look, can we improve our electrodes and can we maybe reduce the K thermal conductivity to improve the reset process. So one solution was proposed to use like a combined target. Here we have titanium nitride, titanium aluminum nitride, and if you use another elements, like in this case this was C16, and again the thermal conductivity of titanium aluminum nitride is like 5 millikelvin. Of C60 it's much less, comparable to phase change materials. And now there are also some tests on real devices. This is T-shaped device with 4.80 micrometer CMOS. And what they found really that if they use combined electrode with C60, the fullerene, then they can reduce the reset current. This is the thickness of fullerene. This is dependence of the thickness on the reset current. This is the without fullerene, and this is the fullerene, the thickness of on the range of 3 and 5 nanometers. What we can see the change and the reduction of reset currents for both type of electrodes, titanium nitride, titanium aluminum nitride. Then we also see the increase of air set of crystalline, so also which is good then for reset operation. And also here there is a reduction of energy consumption. The endurance here is like 10 to the 5 cycles. Maybe can be improved in further research. Another site where we have some losses in the material This goes also by some interfaces in the cell. If we consider our phase change device, like consisting of metal, GST, and bottom contact electrodes, when we have here different interfaces, like here between metal and GST, between bottom contact and GST, and also this is silicon oxide and GST. And these all interfaces and boundaries, they make like so-called thermal boundary resistance. And this is the thermal boundary resistance between the heater and the GST. This is very important because the bottom electrode dissipates most of the heat during programming, and the TBR arises from the partial transmission of heat carriers across the interfaces. So we can look to this TBR in GST. This is the interfaces conditions here. They consider it by using this equation. There this heat flux through the interfaces. It's given by delta T, and this is RTH, this is the thermal boundary resistance, and this is equal to the change of the temperature and to the thermal conductance of the interface. Actually, this G can be measured experimentally. I will show you later. But some calculated programming currents. You can consider your system, and you can change the conditions, like to take into account the thermal boundary resistance or without thermal boundary resistance. Here one example for GST without taking into account thermal boundary resistance, and this is for the cases where we take this parameter, and also here this is the value of different value of thermal boundary resistance, changing between 0 and 100, and these are curves they show for the different thicknesses of GST, which is also can influence the programming current. And what we can see here that the programming currents, they are reducing if we take into account this thermal boundary resistance parameter, comparing if you don't take it into account. This also programming current here, you can see it also depends on the thickness of the GST layers. Like for higher, larger thicknesses, it's less current needed for melting than for thicker thin films. Now, if we go to our example here, one effect was that we reduces the K thermal conductivity at the interface between the bottom electrode and GST materials. This was one effect, but another effect was also the reduction of thermal boundary resistance. Here the thermal conductance was measured thermal conductance and against the thickness of fullerene layer, and what we can see, if we increase the thickness of fullerene layer, then this G parameter it increases. It decreases here, and for our system with for example with GST C60, then it's triangles here. It's increasing. So for titanium nitride GST, the thermal boundary resistance, it's like if you recalculate, it's like in the range of 20 M2K GB, and this gives our G around 50 MV M2K. And if we introduce here this fullerene layer, then we can see that the thermal boundary resistance is increasing a lot, and so seems to be that large TBR contributes to these low reset currents. So the combination of low KPC and FK materials might also increase this TBR, and as we also have seen for composite materials, this is not only effect of nucleation on the new phase or oxide phase, but also oxides, they have low K than PCM, and they can also effectively increase the thermal boundary resistance and decrease the reset currents. So this is one way how you can improve your material or device on material side. Also, one idea was to also proposed in the literature to use the thermoelectric layers between the titanium nitride and GST, and here they tested in the mushroom cell configuration, and they found a huge reduction of the current density, reset current density, which is on the average of 10 MA per quadrat centimeter. In the case of pure GST, we will have like the value of 20 MA per quadrat centimeter. So we have here 2 times reduction in reset currents due to this thermolytic layer, which due to the additional thermoelectric heating which caused by bismuth telluride layer. So now let me conclude this part of my lecture. So the topic, we defined the topic like the introduction of more on one elements in a small amount. This is on this average 10 to the 7 atomic percent, and this doping should not change the crystal structure of the current phase. In the case of GST, if you introduce 20% and 10% impurities, they can be introduced to the GST, but if they do not change the crystal structure, we can talk about doping. In all cases, we will talk about the alloying. And alloying, this is the formation of solid solution of two or more materials, one of each is metal. And if you have the precipitation of secondary phase in the alloy, secondary means the main phase, this is GST, and another, this is not GST phase. Then we will talk about the composite, which would be a mixture of materials which has different chemical and physical properties. Dopant introduction into the phase change layer can be achieved by different methods. We considered these elements, pin-block elements, which increases the thermal stability of amorphous GST, and they increase also data retention for nitrogen dope and C-doped by lower switching currents for C-doped GST. Real PCM devices based on oxygen GST show all cell characteristics required for CMOS integrity, while this carbon and nitrogen doping not. The transition metal dopants like chromium, titanium, they improve the thermal stability of amorphous GST by increasing TC and EC, and they increase the data retention, temperature. Post transition metal dopants like zinc increases optical backup in addition. Reasons for stability of amorphous phases, the topic element reduces the number of 4-fold AB rings, it reduces the formation of bonds. So germanium-rich GST alloy, they can also improve the thermal stability a lot. They also increase 10 years data retention, temperature, reduces the reset current, amortization current, and they have also large reading window, and stay stable at higher S after 100 degrees C vaping for 6 hours. And this is one of the main candidates for for automotive application. Composite alloys, they reduce thermal conductivity and reset current, as well as increase thermal stability, data retention, and endurance. And TBR packs E reset larger than K, and electrodes must be carefully selected to increase this TBR without degrading electrical properties. So now I will go to the last part of my lecture, lecture. And today here I will consider heterostructured phase change materials. We have already started to see for some so-called superlattices and their performance that they are very advantageous in the sense of lower energy consumption, also endurance. And here I would like to show you maybe more examples and to discuss some interesting feature of these materials, like local structure, also the switching characteristics, also switching mechanisms, how they operate, because this is a really hot topic, still hot topic in the phase change community, and many groups are still working on such heterostructured phase change materials. So first of all, let me define what are heterostructure. Heterostructure is combined word. It consists of hetero and structure. Hetero from Greek means other, and other is different. So, and here if you put this like different structure or another structure or other structure, we can define the heterostructure like a layered structure consisting of different structures. It can consist of solids or amorphous parts as well as their combinations. Here, this is one example of different heterostructure. If you take like Lego and combine the different stones of Lego stones on each other of different color, we can obtain like similar heterostructured materials. There is also another definition of heterostructure. This is superlattices. And if you talk about superlattices, these are crystalline heterostructures, consist of crystalline layers. And these layers, they have to be grown epitaxially on a substrate like silicon or another. They have also periodicity on both scale of nanoscale, like they are between several nanometers, but not exceed 100 nanometers. And such heterostructures, they can be grown by different methods, like MBE, sputtering, PLG, or ALD. So different PVD methods. So why these heterostructures, particularly superlattices, are very attractive? Because in the first publication on the superlattices, it was in 1211, and they combined germanium telluride and antimony telluride as superlattices, as highly crystalline layers. And the idea was here to combine the two materials with different physical properties. The germanium telluride, it has higher thermal stability but low switching speed times. On the other hand, antimony telluride, it has low crystallization temperature but high switching times. And so if you combine it in one stack, in one superlattices, you can benefit from these two properties, physical properties. So maybe you can get a material with high crystallization temperature and high switching speed. So this was the idea. And the idea was also to grow antimony telluride as crystalline SBT and crystalline germanium telluride. And also they want to grow this like in quasi-van der Waals manner, so just to get some gaps in between. In this my talk and in this lecture, I will consider if the structure, if you grow such superlattices, you can get the same structure as you want, and also I will consider the mechanisms, because if you have such crystalline lattices, you can think about you can bring your system from low resistance state to high resistance state simply by atomic movement, similar to the ferroelectrics, like by changing the crystal order, local structure, and we will look if it's true or not. And in this case, if you can move your atoms from one crystalline to other crystalline state, you have no resistance. You have no resistance drift. So this problem does not exist anymore because you are crystalline state, and then you don't need the amorphization. So again, crystalline transition, and you need less energy to trigger this, to operate this device. But again, the question, let us consider if it's true or not. So as I said, the first publication of the hetero-structured was dated 2006. It was made like amorphous superlattices. Hetero-structure consisted of amorphous layer because they were deposited at the room temperature. Germanium telluride, antimony telluride. They showed some the endurance to the 10 to the 5 cycles. They also showed reset times for such heterostructures. Low reset currents also compared to the tested GST PCM cell. They explained this effect by the better heat confinement in the superlattices recording area. So they did some calculations, GST25 superlattice, and you see here the heat distribution in the working area. This is very large, here it's small confined, and they explained the better performance in the sense of shorter set at reset times and low reset currents by low thermal conductivity of such heterostructures compared to GST PCM devices. But here again the endurance is still a little bit an issue. And then in 2011 there was a Nature Nanotechnology publication, and they showed here improvement of this parameter endurance in 10 to the 9 cycles. What they did, they grew really highly crystalline or textured superlattices. So here is amorphous, here we have crystalline superlattices. They found also low currents and energy for switching of such supercells compared to GST, and again improvements, huge improvement in the endurance and low operation energy and low currents needed. Here they explain this by reduced entropic losses associated with the phase change process. So here again they explain this by the atomic movement at the interfaces. I will consider more on this. And so if we have in simple words, they explain it like by crystalline transition, and that is why we have this low energy consumption of such superlattice devices. There are also some further studies and research in this direction to see the reset current density of such crystalline superlattices. This is like 2025. They showed reduction of current density, reset current density to the value of 3 MA per square centimeter, and this is like for GST again, it's between 20 and 25 MA per square centimeter. They also found the reduction of thermal conductivity of such GST, of such superlattice cells. So we can see here for amorphous FCC and hexagonal, but we use amorphous and crystalline FCC. So we see differences in the thermal conductivity. For AGST it's low, for FCC it's a little bit larger, but for superlattices, it's for crystalline, it remains on the range here 0.4 W per MK. So this also brings that the thermal boundary resistance of such superlattices is larger compared to the GST. This is like maybe 50% increase of thermal boundary resistance. And all of these parameters somehow to contribute to this superior performance of such a cell. But this also cannot be explained only solely on the small thermal conductivity of these cells, because the thermal conductivity of SGSTs is also lower. But this can be some explanation, some idea that low thermal conductivity, a large thermal boundary resistance can contribute somehow to the low power consumption of such devices. Now let us look maybe to the idea of low entropic losses. If we have crystalline layers consisting of germanium telluride and antimony telluride, we can get to the idea that the high and low resistance state can be obtained by different arrangements of atoms at the interface or in the superlattice. So let's start with the model of such a superlattice. Like this part is response to the antimony telluride. These layers, you should stack the superlattices with very thin thickness to achieve the composition of GST 2 to 5 alloy. And so it brings to the thicknesses of the layers like on the range of 1 nanometer of germanium telluride and like 1 or 2 nanometer of antimony telluride. So here we have 2 unit cells of germanium telluride and 2 unit cells of antimony telluride. And now we can consider here this is the germanium telluride, and we can think that the switching it's based on the changing of the position of germanium atoms at the interface. This is germanium, this is also germanium. And now we can create different structures, like here the germanium like flick here to this point and create a new structure, like Petrov structure. This is inverted Petrov structure, where we allow to move germanium back to the empty side. And then this is ferro-GET, where we have like different local structure, where we have tellurium, germanium, and tellurium, germanium. Here in these both cases we have germanium, tellurium, vacancy, tellurium, germanium. And so based on these models, you can calculate properties using simulations. And this structure, so-called ferro-GET, it can be like a set state, inverted Petrov, like this structure. This is also attributed to the reset state. This is one model proposed by Dominaga. Another Onyage model, they proposed that Petrov can be a low resistance state, and the inverted Petrov can be a high resistance state. So just somehow in line, but here this is the little bit different models. So Here also there was some theoretical estimations how these both models can operate and if they can be like if they're feasible or not. For switching of such between these models, we need two-step process. One is vertical flipping of atoms and then the movement. So here you need to consider some energetic considerations. So if it's feasible from energy point of view, thermodynamic point of view or not, if you can move the atom, flip and then move. So you need to calculate like so-called energy barriers by first principles. And here there are estimations for model 1 and model 2. Some seems to be like the model 2 is more energetically favorable compared to model 1. But the problem is that the atomic flipping type, if you do some estimations based on the rate coefficient of flipping, which is defined by like k equal to a exponential minus a divided by ABT. A, this is the vibrational frequency of atom, and if you set temperature 900 K and EA like 2.456, which we know from experimental data, then we can find that the flipping of such atoms, it requires like 52 seconds, and this is too long to operate by this like by atomic movement. So this is very long for data storage. Now the question is, can we look first to the local structure of such superlattices to find to adjust maybe theoretical simulations and models, because here in this publication they claimed, they are crystalline, very well crystalline, and that's all. They consist of like Van der Waals curves, but there was no real studies, local structure study of these superlattices. Then several years later there was publications of Koi on microstructure. They showed the formation. They showed that the structure is different. And let us look to this. This is our experimental results. We also reproduce such epitaxial superlattices. This is like a basic research. We were not aimed to use very thin film films. We want just to know the basic properties of this system. If we deposit thicker film films, like between 10 nanometers and 7 nanometers of germanium telluride and antimony telluride, and they can also vary the thickness of such layers to see the effect of thickness on the local structure of these materials. Also, we can use just different growth and temperature. In the superlattices in magnetrons pattern, they are produced on amorphous substrate, and they require a little bit higher temperature on the range of 230 degrees C. We also varied to the temperatures, starting from 100 to the larger, higher temperature, to see what happens with the microstructure of such superlattices. And this can be achieved by PLD growth on silicon substrate. As I said, we can start with very low temperature, with 100 degrees C. We can grow these periodic superlattices, as you can see here, antimony, germanium, antimony, and they all correspond to antimony-rich layers, to germanium-rich layers. Here also the same. So first, what we can see here, we can somehow distinguish between different layers. And here the composition of each layers, like to this thickness, they are somehow intermixed. So here we have not single layer, but like a mixture of antimony, germanium, and tellurium. The tellurium stays constant during the growth in the thin films. So here we see that the germanium-rich layers there contains like 40% of germanium and up to 10% of antimony. Here, this is also the signature, first signature, that antimony is highly diffusive in the system and can diffuse into the germanium layers. And the reverse process can also happen, we will show later. And here the composition of germanium layers, here you get more antimony. So with increasing temperature, antimony diffuses more and more into these layers. By considering the local structure, the high resolution images, we can find really large blocks of such germanium-rich layers, and here in this case, very thick blocks. And if you do the local structure analysis and chemical analysis by EDX, we found that there is a lot of antimony in these blocks. So these are not solely germanium telluride blocks. These are like a mixture of germanium, antimony, and tellurium. More antimony forms close to the antimony telluride blocks, and less in the center of this block. If they increase the temperature of golden temperature until 185 degrees C, we found also huge changes in the microstructure. Here, the germanium and antimony intermix more and more. In some grades, we found even the formation of stable trigonal phases. And if we reproduce the structure which were published in the literature, like also by using very thin films of germanium telluride and antimony telluride. Here, this is EDX maps. It shows that the layers inside are fully intermixed. So instead of formation of germanium telluride, we have the formation of germanium antimony telluride material. Here, if you look to the local structure of such superlattices called at 185 and 200 centigrade, first you see the formation of such building units with 7 and 8 tellurium layers. These building units, they correspond to the antimony telluride. We have like dark lines in between. These are van der Waals-like depths. And if you make local analysis, elemental analysis in such blocks, you can see that all layers inside of such GST blocks, they are all intermixed, so they contain germanium and antimony. At the temperature of 200 degrees C, we observed the formation of 5 tellurium blocks and 4 tellurium blocks, and these blocks they are already very close to the GST 225 or GST 124, so the composition of such a block very close. So what we see here, we see a very huge intermixing in this system. So germanium and antimony can diffuse between the layers and form germanium antimony telluride units. So what we can study from this and what we can learn if you want to grow such a periodic system that you assume I want to grow antimony telluride and germanium telluride layers, individual layers, you will never get this, because due to this high diffusivity of germanium and antimony between the blocks, you get at the end of antimony telluride blocks, they stays in the system, maybe with some amount of germanium, but there are no germanium telluride layers in the system, so it's fully intermixed GST blocks. So the idea of to use like local rearrangements of elements of germanium, it does not work anymore. So we need to think about how the system, how the switching can proceed in this system. Maybe there are another idea, maybe there are another switching models. And the next also question, how to count the intermixing like this, and the presence of structural defects, because in this system and the superlattice case, you can find also a huge number of such bilayer stacking faults, which are also observed in single-phase materials. But here, this is also the intrinsic properties of such superlattices, and the question is how can we take it into account, and how can we consider it? Can we think about the new models, new switching models? Here's one idea. It was done in 2018. They compared the ordered structures, GST structure, and disordered structure in the superlattice, like this superlattice, to see if there are differences between in the density of states. First of all, they constructed a perfect lattice based on Cohen model. Then they start to make a model with some intermixing of the layers, cation layers, and then some layers with substitution of germanium and antimony. And so first what we found, we see that the whole structure they possess well-defined band cap, but because the density of states shows that the Fermi level shifts down to the valence band, and the bands kept like for such system, it's like in the range of 0.6, 0.4, and the superlattice is still semiconductor. So it seems to be that because there is no change in the band cap, it seems to be that intermixing is not the reasons for changing of electronic properties, because low resistance state and high resistance states should be different, like in the band gap and density of state structure. So now let us change the composition of such superlattices, like to adjust, like this is also made by computer simulations. So what they created the ordered GST124 with antimony telluride, and then they created a building unit, integrated building unit with non-stop geometric composition, like they took one layer of antimony and attached to the antimony telluride, and it changed the overall composition of the system states, but it changed the local composition of the system. So here we have instead SB2 to level 3, we have here SB3 to level 4. And so now if they make like density of state calculations, we can see that if we use stoichiometric structure, when we have here one state, and if it's non-stoichiometric, the loss is changing. So here we have like again transition to the non-metallic to metallic phase, which has without a band gap for non-stoichiometric model. So it seems to be that the electrical properties of such superlattices, they can be tuned by the local composition. Also, electron counting model also shows some differences between stoichiometric and non-stoichiometric model. And this, according to this electron counting model analysis, the net charge transfer within the formula unit of the material should be 0 in order to hold a band cap. For stoichiometric model, if you take it, this is actually 0. But for non-stoichiometric model, for upper block, this is -1. So the electron deficient, this is p-type tendency. and for low block we obtain 1. This is p-type also tendency. It shows also that there is differences in the electronic structure between two states, but it's based on the local structure change in this system. What is the mechanism behind of this? How can we locally change the structure? It's based on the consideration that we can introduce such a bilayer taken fault into the system, and if we allow to move this bilayer taken fault, we can change the local structure of our system. So we know that the staken fault, bilayer taken fault, this is the change of the height of building blocks from one side to the another side. So here we have antimony units close to the van der Waals like that here also. And now if we allow to move this bilayer taken fault to the right, here we flip the atoms goes to the van der Waals like that. And then if they move, then at the end we have one part of our crystal which has non-stichometric composition. So again here we have more germanium, and here we have more antimony, and this state, like again, it's a more metallic state. So we have a transition from one state to the another state. This is also everything nice to have it in the computer to make these calculations. But can we also see it in the experimentally? I was also to note that this is one of the model of such bilayer taken fault motion. I considered only one. There is another one proposed by Kolobov and Pomiganaga. We also consider this non-stichometry in the GST blocks, but I will not consider to today in our lecture. If you're interested, you can book it. Very interesting papers, but the idea almost the same, that there is some local stichometric changes in the system. This change of the local chemical composition can be actually shown in the experiment. You know a little bit about this. I showed it in the second lecture, but just for recap. So if we have such a building units of GST consisting of 4 tellurium or 5 tellurium layers, and these are vacancy spaces like van der Waals like cap, we can induce these local chemical changes by using electron beam. So if we just exposure these layers to the electron beam, we can change this, change the local structure and local composition. So here we have antimony-rich layers on both sides of the van der Waals like that. And then if you move these layers to the van der Waals cap, we have here more antimony-rich layers, but here these are layers germanium-rich, which are sitting here. And then this process is reversible here from one state to another state. If you expose this van der Waals cap, you can go back to the system. So of course these are not one-to-one processes which we have in PCM device. In phase change device, we need to apply electrical current to switch from one state to another state. But this is like a basic results from basic research. It shows how that the system can be flexible, very flexible. So you can induce these local structural changes in the system on the nanoscale change, on nanoscale. We can also confirm that if you induce such a local chemical change, we can also make and create such. You know already these are bilayer taken faults. Such bilayer taken faults, they are mobile. Again, we can create such bilayer taken fault here with the size of 2.5, and we can allow to move this taken fault to the left, and this is exactly how this theoretical model considered to the change of the local chemical composition in the such chalcogenide layer materials, so by moving of such bilayers taking falls. Again, it's confirmed to some extent the model, but in the PCM device can be a little bit different. So also some defects in the superlative system. One, we consider it's bilayers taking falls. There are also formation of vacancy layers in this system. This is this layered structure, germanium antimony telluride, consisting of different building units. And if we heat up this system into the TM, to this temperature, 240 centigrade degrees C, then we can see the formation of the vacancy layers. So such thick building units with 60 aluminum layers can be decomposed to the smaller building units with 3 aluminum layers. And here the vacancy layer can be formed. This is also a reversible process. You can reverse it to the initial structure, again by feeding these vacancy layers by the atom. Again, it shows very flexibility of such a system. And here we expose this part, this area, and transform only one part of the building units to the initial state. And again, if we here expose this part, the vacancy layer, we can bring the system fully back to the initial state. This transformation, let's say crystalline transformation, also is connected to the changes of the distances in the system. So if you have here such a vacancy layer, we have increase of the distances between tellurium layer. The distance between such van der Waals like kept there a little bit smaller, as you can see here. So we see that we just expand our material, our units, so we bring somehow tensile strain, so some strain into the to the structure, so we expand the structure. If you like fill the gaps again, the distance is getting much larger, and so it brings back to the initial structure. Here, sorry, it was wrong. So the distances here reduces. So the building units, they are contracted to each other here, and here we have expansion of the building units, and here so can induce some strains into the building units, and here again we can relax it. Also very important information if you want to consider some new switching models. Here this is also the system, the vacancy layers, and by exposure these vacancy layers, we can fill them and transform to another structure, or we can form vacancy layers in the superlattice. This is antimony SBT units, and this is GST. If we just expose some units, some layers in this GST block, we can write the vacancy layers here and decompose the block, and then we can, if we expose again here by electron beam, we can bring the system back. So this old information can be also useful if you want to consider another switching mechanisms as proposed by our publications. Here they consider the partial homomorphization of such vacancy layers, so van der Waals type F. So if such process is going on in the system, then you have a change of the directive function, or so there is a reduction, and then this is for crystalline. This is higher, this is lower, so it shows the changing of the physical properties of such a system. Another model which also can be considered, because we have seen that they can also change somehow strength in the super superlattices by formation of such vacancy layers. Then this strain also can impact the amorphization of the material. So it also was shown experimentally that such superlattices they are strained, and if we make like initial molecular dynamic simulations, such strain units they can be amorphized in the computer. So also such a new idea how this switching can be going on. Unfortunately, this is all everything nice and good. We can talk about such local structural changes. Until now, I have never seen the papers which confirm such a switching mechanisms. There are some data on real switching of PCM devices. One was published 2021, then 2022. Also, there are another several publications, and all this publication they shows if they amorphize, if they apply reset pulse to the superlattice system, to the highly crystalline system, they observe always a transition from crystalline to the amorphous phase. Here, this is amorphous. Here, in the publication, they claim that there is still maybe some this is amorphous phase, but here they claimed that if they go back to the set state, they can use some layering or formation of these superlattices back again. Unfortunately, I cannot see it. I cannot see these layers in this image. But anyway, the both system they have showed high endurance here, very nice switching properties, low power consumption, and low current density switching. But here we see that we have transformation from crystalline superlattices to amorphous superlattices. The only difference is to the single phase material that we still have here some crystalline GST or superlattice which has very low thermal conductivity, even lower than FCC phase, and maybe it could be the reasons for the lower reset times, that the energy which can dissipate much faster to the sides of the working device. That is why we can get shorter switching times. Also, there are some discussions on that, if it's true or not, but the experimental data I showed you, they show that the superlattices, they have low thermal conductivity on the level of amorphous phase. So now also some advancement of superlattices. Here they were produced in standard CMOS technology using silicon nitride and heater titanium nitride. Such superlattices can be also produced on flexible substrate, if you think about flexible electronics. And the flexible substrates, they are always made of polyimide, and polyimide they have very low thermal conductivity. And this is also one reason we considered how we can reduce the melting current and also reset current density. Here this is one device, very flexible device, published 2029 in Science. And this is the structure, superlattice structure. And this is the current density required to switch some device. This is very, very low, so this is on the average 0.188 square centimeters, like in this range, so it's very low current densities. And switching energy like 84 picojoule, and such as superlattices, they have very, very low resistance rates in the range of 0.2. So this is how this superlattices can be used for microelectronic or flexible substrates. So at this point, I would like to start with the results of this lecture, and we have time for discussion.
So, anyone, if you have any doubt, queries, so you can discuss with speaker. The session is open for questions. Anybody? So just in superlattice, this structure which you discussed, so while selection of these different layers, what is the primary thing which we need to understand in terms of material point of view? So that, I mean, we cannot randomly take any layers and we can do something, but in terms of phase change, I mean, if you want to see, say earlier it is already reported with GST, with SB2T3 and GET. So while selection of any new design or new structure, what is the basic fundamental thing which we need to take care about this?
Yeah, this is a good point. But until now, the most used system like GET is BT because of this high crystallization speed and high thermal stability of GET. Of course, there are some direction to replace germanium telluride by GST layer, like 2 to 5, 1 to 4. And also, I did not show here the results, but there are also some results of IBM on switching of single layer GST 1 to 4 of trigonal phase, layered phase, and they showed similar switching characteristics of superlattices. So it seems to me that this layered structure, the van der Waals curves, this is the main point. So you need to increase the density of these interfaces, these vacant places. If you can increase it, then maybe you can get better performance of your cells. But okay, think about that this is not crystalline to crystalline phase change, it's rather amorphous to crystalline. But the thermal conductivity on the sides of the remaining crystalline state is much larger or much lower, which is it gives you benefits of the device. But there is also limitation. If you want to increase the densities, the number of these van der Waals-like gaps, this is either used solely antimony telluride, but the amorphous state is not stable, or you go to the GST 1 to 4. And this is also limited. It has 2 layers, 3 tellurium layers per building units, and you cannot go down. Maybe you can find some in other compositions, but maybe antimony telluride would be nice to have it if you would stabilize it, amorphous state. And, I think this is a nice prospect to use antimony telluride.
Thank you. So, yeah, you have a question? Okay.
So in superlattices, we saw that actually in higher temperatures, SP antibody is going up by heating as higher temperature. So while we are going back to amorphous phase, is there any kind of trend, or we can say like that the junctions are like this, or not junctions, the different structures are stacking, right? So is there any kind of trend we can say that antibody will be top if even in the amorphous phase like that?
Yes, it should be, I think.
After next cycle also antibody will be in a top layer only, right?
Yeah, there will be, like, the doping will be not homogeneous, but like heterogeneous. But anyway, maybe it will help if you want to stabilize the face here.
And one more, electron beam we are applying inside the TM only here. Inside the TM.
Yeah.
Institute electron beam applying.
Most on in situ, TM, yeah. The electron microscope, yeah. Inside of the microscope.
So any more questions? If not, then let's thanks Dr. Henry because this we are completed almost our lectures along with tutorial. So now I hope you all got sufficient knowledge and you can further go in this direction. So yes, it is still we have another session in the second half where we will complete our examination. About 1 hour, so there is a change in schedule. Again, I am telling you need to be here at 2:30. To 2:30 to 3:30 we have exam. Then after that 1 hour some discussion and then some evaluation will be there. Then at 4 o'clock we will start our valedictory session where you will get certificate and kind of grade sheet also. Okay, so let's thanks Dr. Henry. Okay. Okay, so just have a break and let's meet at 2:30 here, sharp 2:30, okay? Inform everyone who are not here also, huh? Please, thank you.